So good morning. So before we start, are there any questions from last lecture or about course in general? Okay, so everyone knows that Monday by 10, the project, if you haven't already responded, it needs to be done Monday by 10, so we have a chance to review it. If you're doing option 1, we recommend you submit something a little earlier just to get some feedback so we can sort of tell you whether the project scope is either too big or too little. Okay? And I think option 2 is there's already 2 groups signed up for that. Option 3, there's 1 group, so there's 1 space left for option 3 if anyone's interested. All right? So today we're going to finish our discussion of sampling and aliasing and resolution and talk about how you actually apply it in real-world MRI calculations. And then we're going to spend the last half talking about RF excitation, revisiting that, and then talking about how you do a slice selection, which is a very important concept in MRI. So just to remind you where we were, sort of recap the overall situation, we basically have an object. Okay? In this case, it's just this rect function. And the data we acquire in MRI is the Fourier transform of that object. All right? So if the object was a rect function, the data that's actually coming off the scanner would be a sinc function, and that's the data we would actually store in the MRI system. Now, the sinc function, we don't necessarily want to sample it infinitely finely or go out too far in k-space. So we're going to make 2 operations. One, we have to figure out how to sample. Okay? So there's going to be some delta k of sampling. All right? And that's represented by a multiplication. So the sampling is multiplying by this comb function with spacing of delta k. And then we also do windowing. And that's just multiplying by a rect function. All right? So that's basically only keeping the parts of the data in the center part of k-space and ignoring the parts outside. So when we're done with all those operations, this is actually the data we have. Okay? It's samples in k-space, and it's only samples within some window, because that's all we've decided, that's all we have time to collect. And from that, we want to reconstruct our image. All right? So we want to understand what is the actual image going to look like. And because we multiplied in one domain, we're going to convolve in the other domain. Yes?
So if we're only going to take the window for that amount, why are we even collecting all that data? Like, can't we just simply, when we do the MRI and all that, can't we just focus our attention only within the window without having to apply a window?
Yeah, so the windowing is more of a theoretical concept. This is the data we acquire. We only acquire that data. This is like the ideal. Okay, so if you had all the time in the world, and obviously I haven't drawn it out to infinity, but that's sort of, if you could collect all the data, that's what you would collect. But in general, we have to make some trade-off. Okay. So we do the convolution in the object domain. So we're convolving with a comb function that now has spacing. This spacing is 1 over delta k. So that's going to replicate our object every 1 over delta k. And it's also going to convolve it with a sinc function. Okay. So if this has the form rect of k over w, this is going to have the form w sinc wx. All right? So that's basically the form of the sinc function. And so what we're going to end up with at the end of the day is replicated versions of our object that are blurred. Okay? Because we've convolved with the comb function, which replicates, and we can convolve with the sinc function, which blurs. All right? So as long as those replicas don't overlap, we're okay. All right? Because we can just cut out the center part, right, and keep that as our image. But if the replicas overlap, then we call that aliasing, and that's what we try to avoid. All right? So that's a summary of the overall picture. So that's just drawn here in equation form. So this is the ideal Fourier transform. This is multiplying by that sampling function, and this is multiplying by that windowing function. So this is sample and window. So then we end up convolving with the comb function. So this replicates. And then convolving with these guys blurs. All right, so that's the basic picture that we have. Let me see if I can get rid of that. Okay. All right, so to sum up, what are the design requirements that we have to do? So we have to pick two things, or four parameters. We need to pick my delta kx and my delta ky, how much I'm going to sample along the kx direction and in the ky direction. And we have to figure out what's the width we require in the kx direction and what's the width of data we require in the ky direction. So there's only 4 parameters that we need to figure out. All right, and then today what we're going to do is relate those to how do you actually design the gradient such that it accomplishes those tasks. So to determine delta kx and delta ky, those are determined by FOV of x and FOV of y. All right, so it's important to remember if you're trying to figure out the delta k's, then you need to look at the FOV. If you're trying to figure out the WKs, then you're looking at the resolution. So the resolution is how finely do you want to sample in image space. So that's like delta x, delta y. Go ahead.
So you're kind of, in order to look at the field of FOV x and y, you need to go to space.
Can you say that again?
So in order to look at the field of view for x and y, you need to look at k-space, not the space it's actually in.
What it means is, let's say I've determined my field of view. I have a head, it's a certain size. I'd say, okay, I need a field of view big enough to cover that head. Then that will determine what delta k I need. Okay? And then with the same head, you might be asked, well, what sort of resolution do you want? Well, I say, I want a head, normal size head, so I need a FOV of like 24 centimeters, right? And then I want to be able to sample that with 1 millimeter resolution. Okay, so I'm going to have 240 samples this way, 240 samples that way. So that's my desire. That's what I desire. So then you enter that into the MRI system, and then it figures out how to sample k-space for you. So it figures out delta k and WK. All right, and we'll go through some examples of that. So the design rules are fairly simple. Delta k is simply determined by this set of equations. And then for your design problems, you can just always set them equal. Okay, we just go right to the limit. So for example, if I know the FOV is equal to 24 centimeters, let's say the FOV of x, then I know that delta kx, I can just set it to 1 over 24 inverse centimeters. Okay, so it's fairly simple. And same thing with the WKs, we can just set those equal. So let's say the resolution I desire is 0.1 centimeters or 1 millimeter. Then I know my WKX is just 10 inverse centimeters. All right, so fairly straightforward, but that's what you'll be using. Okay, so then this is actually a screenshot from a GE console, GE MRI console. So just to sort of give you a sense of what people see when they sit down at an MRI console. And so you'll notice here, one field here is FOV. So in this case, the person has entered in an FOV of 24 centimeters. Okay. You don't actually see a place here for resolution on this scanner. Okay. And that's because what we do is we do the frequency and phase, and basically we tell it how many voxels we want in each direction. Okay. So this means that in the x direction, the delta x is going to be equal to 24 divided by 256. Okay, because I want 256 voxels along the x direction, which is what we call the frequency direction, which we'll go through and again. And then the phase direction, we want 128 samples. So the delta y here is 24 over 128. Okay, so that's how. Now in this class, because we're not vendor specific, we'll just tell you what the resolution is typically. But if you're given the FOV and the number of voxels, then you can just figure out the resolution as well. All right? And in this case, so this is FOV of x. And in this case, the way they set phase FOV is it's sort of like a multiple of the frequency FOV. So in this case, FOV of y would also be equal to 24 centimeters. All right. So the user enters in those parameters. That they enter in what sort of they desire for their image, and then the software just always does the calculations, similar to what we'll do in a few minutes. All right. Okay, so what we're going to do today is we're going to focus on the spin warp pulse sequence. It's not the only pulse sequence, and on your homework you'll do other types of pulse sequences that go through k-space differently. So one warning is the computations we go through spin warp are correct, but they are sort of specific to spin warp. For the homework, you have to sort of think about, well, what are the principles that are the same, but you can't just apply what we do here directly to the homework. You actually have to think about, the fundamentals. Okay, so that's just a warning because typically there will be some subset of people who will try to just take the spin warp stuff and apply it to EPI. It's not quite a one-to-one. You have to think about it a little bit. All right, so hopefully that'll save some people some time. So here we go. So this is a spin warp pulse sequence, and remember in spin warp we're acquiring line by line by line by line by line. So we're acquiring one line at a time. Okay, and so there is distinction between the directions. So in the x direction, this is x, let's say this is y. So, sorry, this is k sub x, k sub y. Okay, so we're going very fast along the kx direction. So in a spin warp sequence, we typically go through that in maybe 2 or 3 milliseconds or less. So that's very fast. Okay, so that's the fast direction, and that's also called the readout or the frequency direction. And it's called readout because basically, as fast as the data is coming in, we're sampling it and reading it. Okay, so that's the readout or frequency direction. So that's the fast direction. The slow direction in spin warp is the phase encode direction because that's the interval between the lines. And that can be as slow as 1 second or more. It can be as short as 30 milliseconds. So that we'll talk about later how we determine that repetition time. Okay, so next week we'll talk about why do we pick certain repetition times to enhance certain features in the image. But for today, just know that that's every line, between lines, you have to weight this TR, which again is determined by the user. So for example, in this case, let's see, what did they set the TR to here? They left it blank, but that's where you would fill it in. Okay. But they did say the minimum TR here is 5 milliseconds, which is super short. All right. Okay, so then basically, for each TR, we have an RF pulse that excites the magnetization. And we assume after the excitation that we're at the center of k-space. Okay? So then we use these sort of what are called D-phasers that they take us out from the center of k-space out to the start of the line. All right? So for that first repetition, I go from the center of k-space out to there. And then this readout does that action. That covers the k-space for me. Okay? The second time, you notice that this is a little smaller in amplitude, so it doesn't take me as far out in the ky direction. Okay, but after I'm out there, the readout gradient does the same thing. So you notice in this case, the readout gradient is the same for every rep, and it's only the phase encode that's changing. Question?
Well, so on the GFX, will the readout, that initial readout frequency or pulse, take it to 1/2 of the window width? Or 1/2?
Yeah, so that's a great question. So ideally, right, it's going to take it out to minus WKX over 2 minus WKY over 2. That'll be the starting point for that for that one right at the corner. Okay. Is there a question there?
Yeah, is there no decay in the KY space during the readout frequency, or is that just too fast?
There is, it really depends on the tissue, which we'll talk about next time. For certain tissues, yeah, the decay can be very fast. But for most tissues, like in the brain, the T2 is maybe 100 milliseconds or 50 milliseconds. So if you acquire it within 2 or 3 milliseconds, you're okay. All right. Similarly here, there's no readout gradient, so we just stay on the axis of k-space and go there. Here now it's positive, so we're going to move out in this direction, and here it's even more positive, so we move out to here. Okay. So those two initial set of gradients is determining the starting point, and then these gradients here are determining that line across k-space. All right, so that's basically what you need to know about spin warp. So this is a different picture, so the top 3 rows are the same, and now I'm just drawing the kx of t and ky of t trajectories. All right. So you notice the kx of t does the same thing every time. It just goes out to some part, some negative part of k space, and then zooms back across linearly to the positive part of k space. So in this case, we could write that we want to go from minus wkx over 2, in this case, to wkx over 2. So it's always spanning across k space. All right. The ky gradient, you notice, is different each time. Okay. It's going out to some value and then just holding that value for the whole line. All right. And then I've sort of truncated the sort of k space trajectory afterwards because basically we're just not acquiring data afterwards. All right. Okay. So any questions on that? This is sort of the fundamentals of spin warp. So let's now actually talk about how we actually design this and how we actually apply this to real-world MRI. So the first thing we need to do, we're going to do is talk about readout. So we'll do a few slides on this and then give you guys an exercise to do. So the RF signal comes in, and remember it's got this modulation of like an e to the minus j omega naught t term, right? So the first thing we want to do is we want to multiply it. We want to demodulate. And that means multiplying it by e to the j omega naught t to get rid of that term. So that very fast precession term. And the way we do that is we know, well, that's equal to cosine omega naught t plus j sine omega naught t. So the very first step in every MRI system, especially unless it's at very low frequency already, is this demodulation, where we actually, for those of you who are electrical engineers, this is basically mixing down to baseband. Okay? So we want to go from the carrier frequency down to baseband. And so that's the way we do that is it's called quadrature. Okay? So we take the signal, multiply it by cosine, and multiply by sine, and we keep both those values. Right? Those are the real and imaginary parts, or the in phase and the quadrature components of our signal. All right? So that's just sort of for background. For this class, the most important thing is two things. We'll talk about the low-pass filter later, but the most important thing right now is we're now going to sample it with some sampling period of delta t. So as the signal is coming in, we can sample it. Okay? So that's the readout. Right? And then every time we sample it, we store that away. We store the real imaginary number away. That's one point in k space. The next sample is another point in k space. Right? So let's just look at the readout gradient here. So now we know that, so we want to ask, what's the delta k for this actual application? So if the readout gradient has the amplitude of gxr, then all I really care about is, for each sample, how far do I go in k space? Because that's going to be my delta k. All right? So delta k is just going to be equal to gamma over 2 pi times this area. Okay? And that's just equal to gamma over 2 pi times gxr times delta t. All right. So the most important part of this is always this area. Okay. So no matter what pulse sequence you're doing, that's going to be correct. The formula for the area may differ depending on what what pulse sequence you're doing. But in this case, since it's rectangular, it's just gxr times delta t. Okay. So how would we do? So that's written right here. Okay, and then basically we're given the FOV, so we know what delta kx is, right? So we can figure that out. And then typically the design problem is you're given constraints on one of the two of those. So you either solve for delta t or you solve for gxr. Okay, so typically on any problems you'll be given one of those and you solve for the other one. So it's fairly straightforward, but it's worthwhile to go through an example. Let's go through an example. Field of view of x equals field of view of y equals 25.6 centimeters. So delta x and delta y are all equal to 0.1 centimeters. So the first thing you should do when you're looking at a problem like this is figure out, well, how big is my image? So how many voxels is my image? Right, 256 by 256, right? So I know at the end of the day I want a 256 by 256 image, right? So if you knew nothing about MR and you hadn't taken this course, what would be your best guess to how many samples you should acquire in k-space? It's like 256 by 256, right? I mean, that's ignoring factors like complex and things like that. But that's a good rule of thumb that if I said I can give you a 256 by 256 image with only 100 samples in k-space, what should you tell me? Would you like the image I give you? Given what we've talked about, no, but in a few weeks we'll show you why that might actually be okay. Okay? But for now, it's not okay. Okay? All right. So now you actually need all that data. Later on, we'll show you how, with things like deep learning and other new methods, you can get away with. So everything I'm telling you now is classical image reconstruction. What we'll talk about probably in the last week is what sort of advanced image reconstruction, where you can actually go beyond these sampling requirements. Okay? But this is the fundamental, so it's good to know what they are. This is like the speed limit. Okay? Okay, so let's look at this. So we know that the field of view of x is going to give us our delta kx. And this is the delta kx, right? Because it's got the gamma over 2 pi, the gxr, and the delta t. So in this case, you're given delta t equals 32 microseconds. And then so you can just plug and chug. And in this case, you get 0.28675 Gauss per centimeters. Okay, so it's fairly straightforward. So the process is you go from FOV to delta k. And then from there, it's either GXR or delta t you solve for. Okay, so that's all you need to do there. So now let's talk about the resolution. The resolution. So the key part here is the delta k is determined by the FOV. All right. The next thing is the resolution. What does that determine? It determines your WKX. Okay. So basically, how far do I go? So I'm at this point in k-space here, minus WKX of 2. And then I want to go out here to WKX over 2. Okay? So the question in this case is, how long do I have to have that gradient on for? Okay, so I know that I'm sampling at delta t, right? Okay, so without even doing any calculations, and delta t is equal to, what was it, 32 microseconds? So delta t equals 32 microseconds, right? So if I want to cover k-space, and given what I know about my image, how many samples should I acquire in k-space? Yeah, 256. That would be a good guess, right? It's probably 100, 1,000 is probably are not good guesses. So 256 is probably a good guess. So even if you know nothing about it, a reasonable guess would be tau sub x should be 256 times delta t, whatever that is. Okay? So we'll check to see if that's correct later. But for now, we're saying, okay, I know my delta x. I'm given at 0.1 centimeter. So that will let me determine what my WKX is. And then going from this point in here to here, the area gets me across k-space, right? So that area traverses k-space, and that's given by GXR times tau sub x. Okay. I know I just solved for GXR in my previous problem, so now I can solve for tau sub x. All right. So let's do that. So here, delta x is equal to 1 over WKX, right? And that's just equal to gamma over 2 pi, so that's 1 over gamma 2 pi times the area, right? So that's gamma 2 pi, and that's the area here, right? We already solved for GXR, so then we can just solve, now we can solve for tau sub x. And it turns out that if you solve for that, you get 8.192 milliseconds, which is exactly equal to 256 delta t. All right, so it's sort of sometimes nice to do those sanity checks. All right, so any questions on that? Okay, perfect. Then that means you're prepared for this problem. This is a multiple choice thing, so when I open up the poll, you're just going to have A, B, C, D, E, or F. Okay? Yes? This is for participation, but I don't know who participated because I'm not charging you. I'm not making you sign up for poll everywhere. We'll have other things that are, where you have to put in your names. But this one is just, I just want to get a sense of where people are. Okay? But go ahead and talk to your neighbors, and you can enter in your answers in a minute.
we're looking for the amplitude. And then this missing time is this fact multiplied by the area, which as we don't know the shape, we can technically infer it because they give us delta t and they give us the g max. So by putting g max in the t, we should come up with a way. Are we using the window for something? Yeah. They give us a G max and that is which is the so from there, walking on maximum velocity, we might be able to get the arrow, and then we can put any keywords. Or the arrow is given by the wind. Okay, I think we should get yes. So So if this is perfect, so as to this is equal to this. Yeah. So yeah, so yeah. But feels always the maximum. Let me have it. So we have an expression here. We have some and this one we get this. And then we need another one. So it's 1 over 20. Because we're solving this song. This is max, just max in this space. But don't need to use at some point. Yeah, that's what we're using. But we don't know the exact one. Oh, we're not using it. Yeah. Keep it they always no, I don't think so. We can just put them in.
Okay, sorry, let's take a look at that. So most of the votes so far are for F. There are some votes for C and D. Okay, but let's just go through this problem together. since you have some time to think about it. So, so we have this readout gradient, right? And we're worried about this readout gradient here. And we want to figure out the amplitude of this readout gradient, GXR. Okay? And we're given delta t, right? Delta t is equal to 5 microseconds. All right? So we know that as long as we know what delta k is, we just need to figure out this area here, right? So that area is, so we know gamma over 2 pi GXR times delta t should be equal to my delta k, right? So what's delta k equal to? Right, 1 over 20 inverse centimeters. So I'm given that this is 4,000 hertz per Gauss, which is a nice number, GXR, and then I have 5 times 10 to the minus 6, right? So let's do the math. It's 120, 4,000, 5, 10 to the 6. Is that right? Okay. So what is that? That's 20,000 there. That's 20. That's 2 times 10 to the 4, and then this is 4 times 10 to the 5. Is that right? So I'm gonna get what? 2.5 times. Do I get 2.5? Okay. Okay. So the answer is, the closest answer is F. Right? So the actual answer wasn't there, but the closest answer was F. So this was actually right off last year's quiz, okay? So, any questions on that? Yes. Oh, okay. Because there's an error. Yeah, yeah. So, and I just figured that out as I was looking at the equation, at the solution. Yeah. Well, that is the closest answer, though. Right? Right, because 2 is the biggest gradient you can have, and so 2.5 is the closest answer. Yeah. Okay, go ahead. That was last year, so don't worry about it. Okay. Yes. Yeah, so that's why it says pick the closest answer, right? So the closest answer is 2.5, so the closest you can get 2.5 is 2.
Oh, so in theory, the gradient can be like 500, but...
This actually happens in real life where you might have a desired resolution and the system just can't do it. So in this case, if you enter this in, the scanner would say, I can't do this. The maximum I can do is this, okay?
So if you stated that like a lower or a higher or lower resolution, it might be able to do that?
That's a good question. So if I enter this parameter, FOV of 20 centimeters, and the scanner goes, I can't do that, what should you do? What should you do the FOV? Make it bigger or smaller? Okay, bigger, smaller. Okay, so think about that, okay? We want to make delta K smaller, right? Right, we want to make the area smaller, right? So FOV's got to be bigger. Yeah.
Would another solution just be to sample longer? And
Yes.
See if you're sampling at 5 microseconds, that seems pretty quick.
Yes.
The resolution.
That's right. So the other thing is, if the scanner allows you, you could say, well, I wanted that FOV, but now I'm going to make delta T 10 microseconds. So that's the other option. Yes.
If 2.5 was one of the options, would that be a wrong answer?
That's good. I mean, I'm going to avoid this in the future, obviously, but so let's not worry about that. Okay. But yeah, I don't know. I'd have to word it differently. Go ahead.
Just like thinking about it, if you want a greater resolution, how would making the image that you want to see bigger make sense? Like, you get that number of feet, so you want your delta K and K space to be smaller to be more accurate. But like, how does that logically make sense? Image a wider area in order to have more.
That's a good question. I wanted the same resolution, right? And I made my FOV larger, right? So what would I need to change then? Would I have to acquire more samples in k-space or less samples in k-space? More, right? Because I'm making my delta k smaller, but my width is the same to keep the resolution the same, so I'm going to have to go more samples in k-space. So luckily there will be problems like that on your homework, and then there will be problems like that on the quiz. Okay, so thinking about this is actually really good because those will be some subset of the problems will be exactly that on the upcoming homework and on the quizzes, on quiz 2, which is basically what if I did all these things, what would happen? Okay, all right. Any questions? So that, yes.
When was quiz 2 again?
Last day of class here. Okay. Okay, so let's move on to the phase encode. So phase encode, remember, we're doing these lines in KY. So we're sampling in KY. So now we care about is this delta KY first, let's say. So the phase encode is slightly different because there's two parameters. One is, or there's a number of parameters. One is how long we play that phase encode gradient out for. Typically, we pick that to be as short as possible because we just want to get out there as fast as possible. And then there's also, as we're incrementing the gradient, how big to make that incremental gradient, okay? And then also, how many gradient steps do we need? So there's actually 3 things to think about, all right? But let's look at the first one, which is delta ky. So we know that if we give them the FOV of y, then delta ky, we know that. And then the incremental area we care about, this area that we care about, is like the area of one of these guys. Right, because each time we add on that much area. So that's the delta ky. All right, so in this case, the area is just this GYI, stands for like GY incremental, times the width tau sub y. Once again, just an area. So let's do an example. So here, the field of view we were given was, what was it, 24 centimeters, right? In this case, you're just given tau sub y equals 4 milliseconds, and then you just solve for g sub yi. In this case, you can actually get a very small gradient. It's like 0.00224 Gauss per centimeter. And that's very standard for these phase encode gradients because remember, you're just incrementing a little bit at a time. Okay. Now let's talk about resolution. Resolution, remember, is related to how far out do I go in k-space. So that's going to determine how many steps I have to take, right? So without even thinking about it, how many steps should I take in above 0 and below 0? Given what you know about the image. Go ahead. About this, yeah, let's say they're the same number of steps above and below, and then, but how many do I want to take above and below? How many steps should I take? Right, WK over T, but for this specific example, I have 24 centimeter field of view, 0.1 centimeter resolution. So how many steps should I, or is it, what was the field of view? 250, yeah. So I want to take 128 steps above and 128 below, right? But that's going to give me 257 steps. We'll talk later why you can actually skip one of the ones below or on top. But for now, just think about 128 below, 128 above. All right. So let's just unless you're told otherwise, you can, and that's actually what's shown here. We're actually taking 2 steps below, 2 steps above, and unless you're told otherwise, you can just use that for your equations and design problems. So the WKY I get from the resolution delta y, and I already solved for gy of p and tau sub y, and this WKY is just 2 times ky max, which is just this area here, right? Okay. So ky max is gamma over 2 pi times this ky max is given by, with this area, gamma over 2 pi times area. Okay, and then we have this factor of 2 in there because WKY is 2 times the max gradient. Okay. Oops, going the wrong way. So let's take an example of that. So in this case, delta y is equal to 0.1 centimeters. I just plug in that equation where I have the gamma over 2 pi. This is the area, this area. 2 times that gives me the full area, right? And therefore I can plug it in, and what I end up getting is gy sub p, which is this maximum gradient that I have to apply, is just n sub p over 2 times gyi which is equal to 128 times GYI. Okay, so that's just telling me I need to go 128 above, 128 below. All right, so that's what it looks like. Any questions? Great. So let's see. So this is just putting it all together. This is unfortunately, as I look at this, is a really busy slide. So, but let's just work through it. So given a general, well, let's actually have you do this problem first. Okay. So because we just talked about phase encode gradient. So while it's fresh in your mind, now you're doing a phase encode gradient, and I'm assuming this doesn't have an error in it, but I will check as you're doing it. Okay. So go ahead and take a look at that. Okay, let's take a look at this. So right now, the two answers that have been picked are A and C. And one of those is actually correct. Okay, that's good. All right, so remember we have a phase encode gradient here, and we talked about, sort of how we step the phase encode gradient. And so what we're trying to figure out is what is the minimum width we can make this tau sub y. All right. So basically, we need to think about which of the parameters, FOV or resolution, matters for making this decision. Okay? And we're also told that the maximum gradient strength is 6 Gauss per centimeters. All right? So which of the parameters should we be thinking about? Should we think about FOV or should we think about resolution? Resolution. How come? Why is resolution the more important parameter for this problem? Anyone? Right, it depends how far you're going out in k-space, right? So if I have 6 Gauss centimeters to use, I need to figure out how long do I need to have it on to go out far enough in k-space, right? Okay. So now we know resolution. So the resolution delta y is equal to 2 millimeters is equal to 0.2 centimeters, right? So I know my WK sub y is equal to 1 over that, right? So that's what, 5 inverse centimeters? Okay. And I want that to be equal to gamma over 2 pi times tau sub y times, we have, can go up to 6 Gauss per centimeters, and this can go to minus 6 Gauss per centimeters, right? So then I'm going to have times 12 Gauss per centimeters. Okay, that's the full span I can have. That's what this whole area is going to be, right? So then I just solve for tau sub y. So tau sub y equals 5 inverse centimeters over 4,000 over, is it 12? Is that right? Or did I screw up here? Let's see. Is it 12 or is it? Does it give me the right answer? What does that give me? It gives me 100 or 104? 104, right. Okay, so that is the right answer. Okay. Okay, so are there any questions on that problem? Yes. No? Okay.
Well, on a conceptual level, when would we use, if we were looking at resolution in X, I guess we wouldn't, when would we use this versus GX?
So basically, so let's actually go over that. So that's a great question. So now we can go back to this really complicated slide. Okay. So this is everything you need to know. So basically, the GX gradient, right? This depends on FOV of x or delta x, right? So that's basically, if FOV of x determines my delta kx. My delta kx is just my GXR times delta t, okay? So that's the area of one of these increments, okay? And then my delta x is the width, so it's basically how far do I go in k-space from one end to the other end. So that would determine my tau sub x, okay? So that's totally determined by the FOV of x and resolution in x. And then the FOV of y and the resolution of y determines things like what's the size of this gradient, what's its width, how many samples do I take, what's the incremental delta g, things like that. Okay, so that's sort of the overall picture.
So if we go back to the problem.
Yeah.
Oh, I see. This is the phase encode gradient.
Yeah, phase encode gradient.
Phase gradient.
That's right. Okay.
So code gradient, just we should consider it as looking in line.
Yeah, for Y, for a spin warp, it's the phase encode gradient. For X, it's the readout, just by convention.
Gotcha.
Okay? All right. Okay, good. So one last question. This one you actually have to enter in your names, and here there actually are more than one correct answer. So it's a little trickier because you have to pick how many correct answers are there and which are they. Okay? But you guys can do it. Okay, let's take a look at this. There actually are there are 3 correct answers, and some of the groups actually did get that, so that's really good. But let's go through that. So first of all, let's talk about so the user doubles the FOV in the x direction, right? So should we think about read out or phase encode? Read out. So we can ignore these guys, right? Does have nothing to do with phase encodes, right? Because we're talking about the readout direction. All right. So now we're down to how many of these 6 are correct. All right. So the FOV went up by a factor of 2, right? So what happened to delta kx? It goes down by a factor of 2, right? So I have this readout gradient, with an amplitude gxr, and the delta t stays the same, right? So if if delta kx goes down by a factor of 2, that means the area must go down by a factor of 2, right? So what must happen to gxr? It must also go down by a factor of 2, right? So that means H is correct. Okay. So now let's look at what else is going on. So delta k is down by a factor of 2. Has wkx changed? No, because the resolution is the same. It says resolution is held constant. So this is the same, right? So my step size has gone down by a factor of 2, but I have to cover the same span in k space, right? So what must be true? Do I have to have more readout samples? Yes, I have to have double the number of readout samples, right? Because I have to cover the same distance, but my step size is only half. So E must be true. Okay. Delta t is constant, right? So if I'm taking double the number of steps, what must be true about the length of that readout gradient? Must double, right? So E must also be true. Okay, so any questions on that? Yes.
Question on C. When you say the number of readout samples, are you talking about 1 over kx, which is the frequency, like how faster, or like the?
Well, basically, from this end of k-space to this end of k-space, how many steps do I have to take?
So the sampling rate.
Well, the sampling rate is delta t, so that's sort of the increment. But the number of samples is like how many steps do I have to take?
Okay.
Yeah.
So that number of steps is what the length of the readout gradient is?
No, that's C, the number of readout samples.
So is
What's
that
the
one?
length of the readout gradient?
It's just C. It's just number times delta t. So if C is true, then E must also be true if delta t is held constant. Right. So this would be like n read. Right. That's how many steps I take. Right. And this is tau sub x, which is just equal to n read times delta t. Yes.
Is C not then 1 over like your sampling rate, which is just kx? Will that not be the same, or?
C is just like a number. It's an integer number. So what was your question about? Is it 1 over what?
Kx, like the way that I thought of it is that, like I thought that C is basically 1 over kx, or in the frequency domain, like how many samples you're taking.
Oh, I see. So, but what is kx in this case?
It's just the period, right?
Okay, but which kx are you going to pick? I mean, kx is, so I guess I'm trying to get an understanding which kx are you going to use? What's your value of kx that you want to use?
I mean, like I'm not sure if we have kx here. Isn't it just like 1 over the field of view?
So that's right. So delta k is equal to 1 over the field of view, right?
Yeah.
So delta k is related to the area that each step takes. But then wk tells you how many steps. So one way you can think about it is if I have w over delta k, that's the number of steps. Yeah, so maybe that's the concept. Okay, so I have some distance to go. Each step is delta k. I need that many steps. Okay, good. Those are all good questions. So these are the kinds of problems that you should expect to see on the quiz. Okay. All right. So in the last half, I think we'll just wrap up with gradients. So I'm going to just talk about a few things that happen a lot in sort of actual application of MRI. First is sometimes we have to image something that's very long, right? So like a spine. And we know that if we have a very big FOV, so we have a very big FOV, right? And then that's going to determine our delta K, right? So if the FOV goes up, the delta K has to go down, right? So we have to, if we have a very long object, we have to take a lot of steps through K space, and that may take too long, right? So how do we get around that? Well, this happens a lot. For example, when you're imaging someone's spine, you may only care about some, like the lumbar part of their spine, like some section of their spine, but you have all this other area that you don't care about, right? And you don't want to spend time encoding all these spins because that's going to, all this FOV you'd rather not deal with, okay? So the question is, how could you image it? And one of the tricks is by making this always, the long direction is always going to be your readout direction, okay? And let's just explain why that's the case. So the idea is, if I have the readout gradient in this direction, right, then if, like, I want an image here, then the spins up here are spinning really fast, the spins at my feet are spinning really slow, and the spins here are in some frequency range, right? So if I have a way of just picking spins, of only being sensitive to spins in a certain frequency range, then I can literally filter out the contribution from all the other spins, okay? So that's actually what happens. The MR signal comes in, it has all these frequencies due to all these spins, but before I sample, I actually apply a filter, okay, an electronic filter that just filters out all those other frequencies, such that I'm only left with the frequencies from those spins in the area I care about. Okay, so when we do FOV, we've always got this filter on that sort of eliminates those other spins. Okay, so that we actually, instead of energy from all frequencies, we just are able to just capture the frequencies from those spins that we care about. So if you're ever imaging a long object, you always want to have the frequency encode direction along that long object. Right? That's just shown here, where this low-pass filter that we skipped over before is really, really important because it allows us to limit what spins contribute to our signal. So the idea is there should never be aliasing in the readout direction, okay? Because this should get rid of the aliasing. All right. Another thing that comes up is related to just the fact that, remember, when we window in K-space, we're convolving with what? If we window with a rect function in K-space, what are we convolving with in image space? A sinc function, right? The problem is if I have sharp edges, like a sharp edge like this, and I convolve with a sinc function, I get this ringing called Gibbs ringing. Okay? Those of you who are double E's have probably seen this in your electrical circuit classes. So one thing I could do is I could just acquire more. So this is a 256 by 128 image. So I haven't gone very far out in K-space. And so I've got this Gibbs ringing here. So one solution is I can go farther out in K-space. Okay? That makes the sinc function shorter or smaller. So then my ringing is more confined. Okay? It's not going to ring as far out. And if you do that here, there's still some ringing, but it's sort of reduced in space. Okay? So that's one option I can do. But what's the problem with that option? Or I have to acquire more samples, right? I have to spend more time. So I may not always want to do that. Okay? So the other option that happens a lot is what's called apodization. And this is a theme that comes up over and over in medical imaging. You saw it in CT when you had the Ram-Lack filter, right? You had this thing that was going off to infinity and you just chopped it off. Okay? You'll see this if you take the course next quarter, BE280B, you'll see this in ultrasound where apodization is used all the time. And in MR, the idea is instead of just truncating K-space with a sharp edge, we're going to slowly window it. Okay? So now, instead of the Fourier transform of a rect function, we have the Fourier transform of a smooth function, which tends to be smoother. So instead of this sinc function, we have this sort of nice smooth function here. Okay? The trade-off is the effective width of that smooth function is broader. Okay, but what it does is instead of having these overshoots and ringing, we now get this nice smooth transition that's shown here. Okay, so that is a trade-off. But because I'm filtering out those high frequencies, I am losing information. But that is a trade-off that sometimes you'll make. Okay, so if you see that sometimes images, most of the manufacturers will always have some default filter on, and because it makes the images just look a little better, and you have to sometimes try very hard to turn off the filter if you really want the raw K-space that was acquired. Okay, so that's one other thing that happens in real life. The last thing that happens in real life, which we've talked about before, is do we need to acquire the same number of samples above and below 0, right? And it turns out, because if you did, then you'd have to acquire, like, instead of 256, you'd have to acquire 257 lines, right? 128 below, 128 above, and 1 in the middle. It turns out, though, that you can actually skip one of the lines at the top or the bottom. And that's typically done in practice, because the information from the top line and the bottom line are exactly the same. Okay. And I'm not going to go through the math, but just give you a sense of what that is. It turns out that this is related to the fact that, remember when you look at those phasor diagrams, if something goes 180 degrees, you can't tell whether it went one way or the other way. So in that case, when you're at, for a given delta x and number of samples, those outer lines of K-space correspond to that 180 degree flipping. So that means the information at the top and the bottom are the same, because at that frequency, you're at the maximum flipping of the spins. Okay? So it just turns out that if you go and wonder, well, why were they able to skip that line of K-space? That's the reason why. Okay? So these are more sort of things that if you don't know about it, it might actually confuse you if you go into MR. All right. So any questions before we move on? Okay, great. So what we're going to do now is we're going to start the discussion of our excitation, and then we'll finish this on Monday. So just to remind everyone, RF excitation is the process of taking the magnetization that's aligned with the B0 field and flipping it some angle. A very common angle is 90 degrees, but any angle can be you can flip it to any angle. Okay. And just to remind you, this is what it looks like. We use an RF pulse that's in resonance, okay, and that eventually flips us down, in this case, to 90 degrees. That's in the laboratory frame, but that's really hard to think about. We have to keep track of this precession. So it's much easier to go to what's called the rotating frame, in which case the B1 field stays the same and the magnetization just precesses like that. Okay, so that's what we're talking about. So it turns out that, so previously we've talked about the precession. So this is precession in the laboratory frame. Okay. It turns out that you can rewrite precession in the rotating frame, and this is the precession in the rotating frame. So it actually has the same form, but it's got m rotation times now gamma b effective. And so today what we're going to do is introduce this concept of what's the effective field that is felt. Okay. So here's the thing. If I'm a spin in the laboratory frame and I feel there's a field here, and I'm going and I precess around it. Right? So my frequency of precession is gamma b, right? So it feels like there's a field here, right? I'm going around, I'm like, well, there must be a field here, right? But now, in the rotating frame of reference, I'm stationary, right? So in that rotating frame, does it feel like there's a field there? No, it's if almost there's no effective field there, right? Because I'm not, in my rotating frame of reference, I'm not rotating around, I'm just staying still. So it's as if there was no B0 field. Okay? So that's where this effective field comes into play. This effective field is equal to the B field that's applied plus this sort of weird term omega rotation over gamma. Okay? And let's look at what that term looks like. So in this case, we're going to think about there's a big B0 field and a tiny little typically B1 field. Okay? And this is going to be rotating around at omega. Okay, so that's going to determine our rotating frame of reference. Okay, so the contention is if we're on resonance, then the effective field will only be determined by B1. The B0 term won't have an effect on me anymore. So let's look at that. So I've got B1 of t times the I plus B0 k hat so when I write this, and this sort of should have, let's see, yeah, this term here is this term here. So it's basically, this is going to be 0, 0 minus omega hat. So only the k hat term really matters. So I have a b naught minus omega over gamma. And if I'm on resonance, omega is equal to omega naught, then this term just goes to 0. And I'm left with B effective equals just the B1 field. Okay, so that's really important. So essentially, if I'm on resonance, then I don't feel the B naught sort of disappears, and I'm just feeling the effect of the B1 field. Right? So that's shown here, where if typically we've got B1 plus this B naught minus omega gamma, but if I'm on and so B effective is some angle away from the x-axis. But if I'm on resonance, I make this go to 0, such now that B1 is pointing there, and then I just have to think about precession around that B1 field. So it makes my life easier. Okay. So now we want to get into slice excitation. So everything we've talked about so far is if I want to tip all the spins in an object. Okay. But sometimes you only want to look at, for example, one slice. Okay, or you want to go through slices. So for 2D imaging, we need to do slice excitation. All right. So here's the idea. Here are all the spins before excitation. If I do non-selective excitation, then I'm tipping all the spins. Okay. But what I want to do is, can I do selective excitation? Can I only tip the spins in a slice? And it turns out we can. Okay. And we use the gradients to do that. So this is what it looks like. So this is the m sub z component before excitation. It's m sub naught everywhere. After excitation, it's 0 in this region here. The mxy is my transverse component. It's 0 everywhere. And then after excitation, all the spins in some delta z are now have m naught. Okay? So that's what we're trying to do with selective excitation. So what happens is if we plug into that formula again, we now have the same thing, but we have to add this additional term for the gradients if we want to apply a gradient. Okay, so now the gradient, this is all part of the BZ term. Now we think about applying a gradient in the z direction. So we have this B naught plus gamma GZ minus omega gamma. If we're on resonance, these two things cancel out, go to 0. So we're just left with this term. And so we're ending up with a B effective that has a component that's my B1 field, and then it has another component due to my gradient. Okay? So what it looks like is this. Right at the center at z equals 0, there's no added field, so my B effective is all along my x-axis. As I move away from the center, then the B effective starts pointing back towards the z gradient, or the z direction. And so it's not going to be able to tip spins as well. Okay? So basically, I'm on resonance here. So for these spins, I'm on resonance. So I'm going to tip those spins very well. For these spins, I'm off resonance, right? So I'm off resonance here, and I'm off resonance out here. Because the gradient has changed the local B field so that we're no longer on resonance. Okay? So let me just finish up with one video, and then we're going to turn over to Professor McVeigh to go over quiz 1. All right? So this is the last thing we're going to do today. So let me just describe what's going on here. This is what's called a Barton pendulum. All right? And so at some point, we're going to start this ball swinging. All right? So the question I'm going to ask you is, let's say this is 1, 2, 3, 4, and 5. Okay? So which of these balls, if any, are going to start swinging if I start the main ball swinging? Any guesses? So who thinks 1 is going to start swinging a lot after I start that? So this is we'll call this A. After I start ball A swinging, what's going to happen? Will ball 1 swing a lot? Slower. Okay, how about ball 2? And 3? Maybe you like 3. Okay, Professor McVeigh says 3. 4, maybe. Any votes for 4? 5? Okay, there's 0 for 5. Okay, so let's see what actually happens, right? So this is physics, right? So we can actually just do the, whoops, sorry. Let's do the experiment. So at some point he's going to excite A. Let's see, when does he do that? Here he goes. It's like a race between 3 and 4, right? And it looks like it's 2. So 2 has a go to the side to sort of see. 2 is actually the same length as the exciting. So it was sort of a trick question because the angle. But that's at the resonant frequency, you excite those spins at the resonant frequency. All the other spins are off resonant, so they're not going to get excited. So that's the basic idea behind slice selection, which we'll pick up again on Monday. And now we'll turn it over to Professor McVeigh to talk about quiz 1.